In this course, we're going to be using the hardware description language called Verilog. And so what I wanted to do early on is to give you essentially a hello world type Verilog description of a simple exclusive OR gate. All right, so this shows you the structure of what Verilog looks like. One of the things I want to impress upon you is that there's two different things that you need here. There's the design side that actually describes the hardware that we're implementing. So you can see we have something called a module. We're going to call it exclusive OR gate. It's got an input A, it's got an input B, those are wires. It's got an output wire Y, and then there's some logic that we assign. Y is equal to A exclusive OR B. This hat symbol is the symbol for exclusive OR in Verilog. So the hardware description itself is not very complicated in this case. That's intentional. The thing that I want to impress upon you is that what we're doing is we're making a module. And with Verilog, every little circuit element becomes a module. And then later we learn to connect modules together to get more sophisticated designs. So think of this as a module. It's got ports that shows you the boundary between different parts of the circuit. It's got logic. This is the design side. Well, this looks a lot like regular computer programming, but there's some subtle differences. We'll get into that a little bit later in the course, but it's not the same because it's describing hardware. And with, for example, regular programming languages like Python, you have a way of printing the output and looking at the output. You have a debugger that maybe can start running the code and look at what happens to different variable names. There's similar things that happen in Verilog, but we aren't looking at variables in the true computer programming sense. We're looking at circuits. And so since printing is different, you really need something that takes the circuit that you've made and produces the signals that interact with that circuit. So for example, in this module, we had A and B as inputs. Over here, what we have is a test bench that's going to run that module. Okay, so a test bench is in and of itself a module, but it's a little bit different. It doesn't have ports. Okay, it's just got a name. All right, what we're going to need to be able to do is instantiate. That's what this comment line says. Instantiate the design under test. Design under test is an acronym that people often use, call it DUT, like the DUT hookup. So what we have is the XOR gate that we described over here in hardware. We have inputs. All right, I've got an input A in this test bench. That connects to my input A over in the hardware. Okay, and B connects to B, Y connects to Y. And so we've now set up the hardware that we're going to try to test inside the test bench. From there, we have some syntax. We're going to go over the syntax, but the point is I have some code that runs through all the combinations of the signals A and B, like a truth table. We'll talk about truth tables, and make sure that the circuit works the way it's supposed to. So when you go over here to the second tab, you can run this, and what will happen is that as you run it, you step through different parts of the test bench that are controlling the signals. Okay, so here's our hardware. It's an exclusive OR gate. We initially had 0, 0. When I stepped through this the first time, this stepped to 0, 1. Now it's going to go to 1, 0, and then to 1, 1. And we're looking at the output, and we can verify that it produces the output that we want. Along the way, we have this display command that's showing what happens with the different input conditions. So I take A and B, run through the different signal values, and I get the truth table that gets simulated in this test bench. Okay, so we can restart this, press R, and run that again. All right, so again, what we're doing is when I hit this run symbol, we're going through the input combinations. All right, we're running essentially this line of code in the test bench. We're looking at the output. The display line here produces the output. Okay, so we can step through this and see it running and verify that, yes, it does do what it's supposed to do. So I think it's obvious why you need a design. All right, you're trying to describe hardware, but you also need test benches, because how are we going to know whether this works? All right, so you have software test benches that will go through the logic that you've described in your Verilog and make sure that things work the way they're supposed to work. So with no print statement, you have to have a different approach, and that's what the test bench is doing. We're going to get into a lot more details about this, but I wanted to put in your head this idea of a design side, a test bench side, and the fact that you have modules and input signals and output signals. That's the main point of this Hello World example.